Alright, so in this video, we're going to be talking about taking derivatives of power series, okay? So here we're just going to start off with a theorem, okay? If the sum from n equals 0 to infinity of c sub n times x minus a to the nth power, which is just the general form for a power series, okay? If that has a radius of convergence, which is greater than 0, then your function is differentiable and therefore continuous on the interval of convergence. Okay, what this means is that now we can take derivatives of power series, and it's okay to do that. Okay, and I mean, this is basically just going to help us figure out more. I mean, we can describe more functions as a power series, right? That's what this is allowing us to do, and you're going to see some examples of that shortly. So here is an example of differentiating f of x. All right. If we try to take a derivative of this power series here, we have f of x equal to c sub 0 plus c sub 1 times x minus a plus c2 x minus a squared plus c3 x minus a quantity cubed, and that all is going to be the sum from n equals 0 to infinity of c sub n times x minus a to the nth power. Now, real quick here, before I even get into that, this right here, okay, this c sub 0, this c sub 1, c sub 2, whatever, all these are just coefficients, okay? These are just coefficients. These are just things that are coming in front of this x minus a garbage here, okay? That's all that these are. So don't get confused when you see all these notations. It's basically like, you know, for this, you might have a 2 times x minus 3, okay? Something like that, whatever, okay? This 2 is your c sub 1. Something like that. So don't get confused when you see, you know, stuff like that. All right, that's just all that means. Now, if we're to take a derivative of this, take f prime of x, well, this c sub 0 is going to be 0. C sub 1 times x minus a. Now remember, f prime of x means we're taking a derivative with respect to x and not n. Okay, so that's what we're taking a derivative with respect to. I know we have a bunch of different variables here, but we're taking a derivative with respect to x. So x minus a, this will go away. You're going to be left with c sub 1. Here you'll have this power comes down, you have a 2c2 times x minus a to the first power, right? And then here you have a 3 times c to the c sub 3 times a x minus a to the second power, and that's going to go on and on. And here, all right, I'm going to explain this in a second here, but you're going to get the sum from n equals 1, the index changes, now it's n equals 1 instead of n equals 0, okay? And take a derivative with respect to x here and not n, okay? If you take a derivative with respect to n, this thing doesn't, it's weird. If you take a derivative with respect to x, you take this power down, you have n times c sub n times x minus a to the, you lower this power by 1, n minus 1. Okay? Now, we know, okay, great, we're taking a derivative with respect to x. Why did we change the index from 0 to 1? Okay? Well, it's because this constant that we started out with went to 0, and it's useless. So we're not going to include this 0, okay? This is not going to be part of our series because it's useless. Why include it? Okay, we're going to start off with our first term, which is c sub 1. Okay, our first term is going to be the n equals 1 term. Okay, and that is c sub 1. All right, so now we're just going to get into a quick example of how this actually ends up mattering at all. Now, what if we wanted to find the power series representation for this function here, 1 over 1 minus x quantity squared? Okay, well, what we can do is start off with 1 over 1 minus x. And we know this to be equal to the sum from n equals 0 of x to the n. Okay, now we know that this is differentiable because it has a radius of convergence that is greater than 0. Okay, so we can take a derivative here. Now, if we take a derivative of this piece here, this is 1 minus x to the negative 1, okay, we're going to get this function. We get 1 over a 1 minus x quantity squared. Now, all we have to do is take a derivative of this power series, and remember, we're taking a derivative with respect to x and not n. We get the sum from n equals 1 to infinity, right? Raise your index, this is your index, raise it by 1, okay? And now you're going to have a nx to the n minus 1. That's what's going to go there, okay? Now, something to note, all right, something to note. I'll write this here. Okay, note the radius of convergence, okay? The radius of convergence is going to be the same as the original power series. So the radius of convergence of this is going to be the same as this. Okay, this is our original power series that we started off with, this right here. Okay, here we know that r is equal to 1. Okay, that's something we've worked with. Okay, so the radius of convergence of this is also going to be 1. But this does not mean that the interval is going to be the same. That's something that you got to realize. The interval is not always going to be the same. It may be the same in some cases, but other cases it's not going to be the same. Okay, so that's just a quick note. Now we're going to be doing more examples of this in the next video, so definitely go check that out. And that's going to do it for this video. So if this video helped you, make sure to leave a like and subscribe by clicking my icon in the top left. You can also view the playlist for sequences and series and the next video in the series. Lastly, if these videos are really helping you and you would like to consider supporting me, I have my Patreon linked in the description down below, along with some other pretty cool links that you should definitely check out. See you soon.